everybody, welcome back. So this is the third video of my playlist series, Statics and Structural Analysis. And today I'll be explaining about connection, supports, and reaction forces. The two previous videos, there was one about the basics of statics, so that is very basic. And then the second one was forces and moments, where we did like some advanced moments questions and equilibrium. And in this video we will learn what degrees of freedom is, supports, determinacy, reaction, and distributed loads. These will be important. These are like the most important ones in the series to understand the next videos that I'll be uploading soon, hopefully, because these elements will help you to solve for trusses problems. Okay, anyways. So first of all, degrees of freedom. Now, degrees of freedom, that is like, it's something new you probably heard. So in statics, so if you have a body that is rigid, and so therefore it moves as one object, but if that body is going to move, so the degree of freedom is how many ways that body is going to move in translational and rotational ways. So in the previous video, I talked about how translational movement is like up or down, left or right, or any direction, whereas rotational is in rotation. Sorry. Okay. Anyways, so degrees of freedom for each different type of object is different. If you have a 2D body, so that is like you draw a rectangle on a piece of paper. On the question, what you could do is you could move it this direction. You could move it right and left. That's one degree of, that's one translation. Up and down, that's another translation. And you could rotate it around. Okay. So therefore we have 3 degrees of freedom. Now, a 3D body, that is like anything you can find, maybe a cube, okay, a cuboid. So you could move it like this, and like this, okay, because you got like, think about a 3D axis, you got X, Y, Z. These are the 3 translations you could move, and then you got 3 rotations. So what I mean by 3 rotations on each, so you could, if you have a cube, let me actually use something that could help more, maybe my phone, okay. It's not the best example as it looks more 2D, but you could rotate it like this, you could rotate it like this, and you could rotate it like this. You see how many rotations you could do? That is 3 rotations. So for a 3D body, you have 6 degrees of freedom. And now if you have a 2D particle, you'll be like, okay, that's kind of like 2D body, except it don't have rotations. But while it might have some type of rotation, but it can be observed, it's too small, so we just say 2 degrees of freedom. Because remember, when we were talking about particles, a particle, when you assume an object as a particle, that is because you want to simplify it as much as possible to make the calculations easier, depending on what you're calculating. Now here we got 2 bodies. They are unconnected. Each one is a 2D body. And we can add up the degrees of freedom for each one. So it's 3 plus 3 equals 6 degrees of freedom. Now, pins and versus rigid connections. So pins are like, think about a door, okay? Pins, it could be in form of hinge. You have a door and it's kind of like, well, not stuck to a wall, but you know what I mean? To make it connected to a wall, you need a hinge. Now, you have the hinge, you have the door here, and you have the wall, as you see. Now, because the door is a body, then it is 6 degrees of freedom. But now, because it's hinged to a wall, the degrees of freedom will have to decrease. So this 3D body from 6 degrees of freedom, it will go to 4 degrees of freedom. The reason for that is now because you can only like rotate it in 2 directions. Okay, so not 3. And you could only take it horizontal or vertical. So there is a rule, okay, for any problem like this. You will do the degree of freedom of that object minus 2 times the amount of pins you have. So here it's only one object we are taking in account, which is the door. We are viewing it from above, and we would say like, okay, so then that 6 minus 2 times the pins, we have 1 pin, we get 4 degrees of freedom left. You will understand more when we do questions about it. Then we have rigid connections, so it's not a hinge, therefore it can't be rotated anymore. Okay, it can only rotate in one way. They can't rotate in the other 2 ways, therefore 2 rotations are removed and 1 translation is removed, because now these 2 objects are rigid connected together. Okay, so there's another rule for it. You will do the degrees of freedom of that body minus 3 times how many rigid connections you have. We have 1 rigid connection here, so it's 6 minus 3, which gives us 3 degrees of freedom left. Right. Now, what if we have like chains of bodies and pins? So the previous slide, we talked about how to find the degrees of freedom. Now, here is the proper formula that will always help you, okay? So degree of freedom left, we could always find it by saying, first of all, 3 times the number of bodies you have, okay? It also depends on the dimensional, like if it's 2D body or 3D body. Then minus 2 times the number of pins you have, minus 3 times of the rigid connections you have. Let's think of this. Now, usually we just think of it in 2D ways, okay? So if you have 3 bodies and 2 pins, what we will do is 3 times 3, because it's 3 bodies, minus 2 times 2, because it's 2 pins, and we will end up with 9 minus 4, 5 degrees of freedom left. What about if it's 3 bodies and 3 pins? Then it will be 3 times 3 minus 2 times 3. So that is 9 minus 6. That will give us 3 degrees of body freedom. And this will act like 1 rigid body, okay? So that is cool, because like, and then we can have larger systems where you have 4 bodies, pins of 2, 3, 2 degrees of freedom removed. So 4 times 3 minus 2 plus minus 3 minus 2. This is a bit like, you will understand, because there's different types of pins, okay? That's why we have different anyways, and then you get 5 degrees of freedom left. Now we have 3 main support types, and first of all is roller pin. So it rolls, that means we know it can slide horizontally and it can rotate. However, it is fixed vertically, so only therefore we have 1 degree of freedom, okay? So you could minus from it 1 degree of freedom. Then we get fixed pin. Now fixed pin, you get fixed translations, which is both vertically and horizontally, they're fixed. So therefore it's 2 degrees of freedom, okay, that you'll have to remove. And then in incastre, it's like kind of not an English word, I think, is clamped. So the body is completely fixed. Even rotation is not possible. So 3 degrees of freedom is removed. All right, now what we can sum up with all of that is we got connections and supports. Connections can connect 2 bodies together. Supports support a body on a surface. we have now 2 types of connectors and 3 types of supports. And in summary, we have the pin connector. So pin connector, you remove 2 degrees of freedom. Rigid connector, you remove 3 degrees of freedom because then it can't move in any way at all. It's completely rigid. Pin connector, you can only rotate. Okay. Roller supports, now that's a support. There is only one reaction force, and that is the vertical, so it cannot go vertical at all. Fixed pin support, that is like it cannot go up, down, or like right, left. It can only rotate. And then incastro support is like it can't do anything. It's fixed, so that is 3 degrees of away. Okay. And the roller is 1 degree of freedom away. Fixed pin support, 2 degrees of freedom away. Right. Now, after we've learned about supports and connections, then there is something very important to know. Statically determinate, indeterminate, or a mechanism. This is very important for the upcoming videos, hopefully. Now, statically determinate, that is like exactly the right number of degrees of freedom taken away. So it's when the degrees of freedom, right, that is left is 0. After you take away all the degrees of freedom from the supports and the connections away from the amount of bodies, then if it's 0, then it's statically determinate. Okay. And then statically indeterminate, that is when the degrees of freedom left is less than 0. Yes, so it's like a negative. And then if the degrees of freedom is more than 0, then it's a mechanism. But so it is still able to move. And statically indeterminate, it is redundant support. Okay, but the statically determinate, it might not move. So why do we have to know this? It is because actually when we know if a body is statically determinate, then we know that we can solve for the reaction forces or any missing forces directly from the equilibrium equations that we just learned the video before this, the 3 equilibrium equations, sum of horizontal forces equals 0, sum of vertical forces equals 0, and the sum of moments equals 0. We can use all of these 3 and we can find the reaction forces. However, if it's statically indeterminate, that means we need extra equations, which is to find the reaction forces, and that is which makes the case a bit more difficult. Now, a mechanism, the structure has non-zero degrees of freedom. That means it can still move. So you can't use equilibrium equations on that because it can still move. It's more like the reason we call it a mechanism, because it can move. It's like, you know what I mean? Now, we can have the same body, but if we have different supports, it can be a different determinacy. For example, on the first one, we have a body that is supported by a roller and a fixed pin. Now, a body has a degree of freedom of 3. A roller support is 1, and fixed pin is 2. So if we do 3 minus 1 minus 2, you get 0 degrees of freedom, which is great because that means it is statically determinate. We can use all 3 equilibrium equations to find for the reaction forces. Now, on the second one, it is actually instead 2 fixed pins. So you do 3 minus 2 minus 2. That gives you -1 degree of freedom. So it is statically indeterminate. And then we have the last one. It is supported by a single pin only. So it's 3 minus 2, you get 1 degree of freedom, which means it's a mechanism. So it's not in equilibrium in the first case. Now, here we can do a worked example. Okay, so we have here kind of like a body that is supported by an encaster. So it's not roller pin and it's not a fixed pin. Okay, now first of all, we should write down the equilibrium equations. Okay, when we write down the equilibrium equations, now we have the horizontal, it must be 0. Therefore, because we have a horizontal force on the on point A will have to be 0 as well, because there is no other horizontal forces going against it or towards it. It's only that. So AH is 0. Now the total vertical forces must be 0. We have only another vertical force that's opposing it, which is the 10 kilonewtons going downwards. Therefore, AV must be 10 kilonewtons going upwards. And then we have the sum of the moments on point A, which must be 0. So if we find the moment on point A, okay, it must be minused by 10 times 2, and that is because we've got a force 10 kilonewtons down, which is 2 meters away from point A, and which must be 0. That means the moment on A must be 20 kilonewton meter counterclockwise. Okay, because if 10 kilonewton is going this way clockwise, then to keep it in equilibrium, then the moment on A, point A, should be anti-clockwise. Okay. Now I forgot to mention this, which is we did not multiply the moment on A by anything else because it's the reaction moment, so it is a moment itself. You do not need to multiply it by the lever arm distance. Right, now we have here a beam, okay, and we've got it supported by a roller and a pin. First of all, let's see if it's determinant statically. So a body is 3 degrees of freedom, minus 2 for the pin, and minus 1 for the roller. So that is 0. That means we can find the reaction forces. As you see here, we first of all, we use equilibrium equations. So the sum of horizontal forces must be 0. And the only force, the only horizontal force we can have in this case is on the pin, because roller, you can only have one force, which is the vertical one. Therefore, the horizontal force should be 0 on the A. So AH must be 0. Now let's take moments about B. Right, if we are going to take moments about B, then let's take, which must be 0 in the end, let's take anti-clockwise or counterclockwise as positive. So if we have AV, okay, I'm sorry I didn't draw AV there as an arrow, but we want to assume it to be clockwise. So because it's 6 meters away from B, we say negative minus 6 AV, and then we've got force 12. So, and it's 4 meters away from B, 12 times 4, and it's counterclockwise. So we get minus 6 AV plus 12 times 4. And we get AV to be 8 kilonewtons going upwards. Nice. Now, we go to the vertical, because we also have BV. Remember, we need to find the vertical force on the roller. So then we have AV plus BV must equal to 12. Okay, as you see here, we've got one force going downwards, the 12 kilonewtons, and therefore BV must be 12 minus 8. And we got the 8 by finding AV from taking moments about P. So now I have 4 kilonewtons going upwards for BV. Right, but if you have to more than you can't, 3 equations are not enough. In this case, you have a body, so it's almost like statically indeterminate, but there is a solution. We can introduce a connection P between, let's do it between the roller B and roller C. And oh yes, connection can introduce new interaction forces, horizontal and vertical on the P. But if we take moments about P for just one side, so with the fewest unknown, let's take it for the take moments about P for the C area, you know what I mean, on that side. And this will eliminate the pH and PV that you need to know. And then this gives the fourth equation, because the moment about P must be 0. And then we know that if we find the moment about P from the C, then yeah, you could do it. Okay, so there will be always solutions. Right, now frames. So this will be a bit different, but similar to the previous slide, the previous example. We have this frame that is supported by 2 fixed pins, and we have more than 3 unknowns. So we have AV and AH, BV and BH. First of all, let us take moments about one of these supports. Let's take moments about A. And because the moments about A must equal 0, right? The sum of the moments about A. That way, we will cancel out AV and AH. And we will also then have to find BV and BH. Now there is a thing though, which is very cool. It is BH, the force BH, the line of action of it, goes through A. So that also disappears. We end up with only BV, okay? And usually we get the distance between all the distances we need. So the distance between the force BV, okay, and A, then we get the moments of it, and then depends if it's clockwise or anti-clockwise. We add it with the force F in the yellow arrow, and we get the moments about the A, and then we make that equal to 0, and then we can solve for BV. So now we have BV, okay? Now we can find we can make the second equation, which is the forces, vertical forces, some of them must be 0. So now we know that AV plus BV must be minus F. Don't forget the F. Must be 0. So we know F, and now we know BV. So we can find AV. Next, now this is where it's going to be a bit difficult. The horizontal ones. How to find the horizontal ones? It's not as easy. We will have to cut through. You see the frame? You see the horizontal part? We cut through the middle, okay? We add a pin P, okay? We take the moments about one side only, okay? And then we can solve for BH. So let's take the moments of about P, only taking the B side, and that will give us BV times the distance plus BH times the distance, and F disappears, okay, and then making that equal to 0, we can find BH. Then after we find BH, we can find AH, because we know the sum of the horizontal forces must be 0. So therefore, AH plus BH equals 0, then the AH must be the same force as BH but in the opposite direction. So there's a lot, it's a bit too like meaty, a lot to it. But if you always follow these steps, you will always be able to solve the problem. Now here we have a cantilever. So again, statically not indeterminate. However, we can always use additional pins and then use the fact that of moments. We take more moments, about more points that we can add. Kind of the similar concept to the previous ones. So we have here we have two rollers, two pins, okay, and we have a rigid like connection because it's an cantilever, and then it's coming out from here, and then there is no more supports from there. Kind of like an so anyways, which this means that we will have 5 reactions. Now for B, okay, B actually will have only one reaction, vertical, BV, and then C will be CV, okay, so these two. However, A, because A has 3 degrees of freedom, we have AH, AV, and AM. So here we have 5 reaction forces we need to find. Well, we always know, always write down your basic ones. Sum of vertical forces will always be equal to AV plus BV plus CV equals 0. There you go, you have one of them. Then, oh, sorry, I forgot the 3 kilonewtons, minus 3 kilonewtons, then it will equal 0. Then you get the horizontal forces. The only horizontal force you have here is AH. So the sum of that, AH must be 0. And then we have the moments. So we still didn't find the vertical AV, BV, and CV. We know AH must be 0. So we will need to create more equations. If we put P1 and P2 and we take the moment about every, like, make a moment equation, which it will equal 0 for some of the sides, pick which side you want to do. You will have more equations, hopefully, and then you could use it as a simultaneous equation, for example. Right, now, what about if we have a load? So what we have done, we've done forces that go either like in a direction, right, in one direction. That is not distributed. Usually, actually, that is just an approximation. You will see what I mean on the next slide, but when we draw a force, we draw it as a line on an object or on a body. And this type of force is more of a good approximation, but most of the times it is distributed. So you could have a load or a force distributed per volume. So for example, when you have a material, okay, with the density, you can have it distributed on area, or you have fluid pressure. You can have it distributed by length. So uniformly distributed load along a beam, which is what we're going to look at now, okay? Newtons per meter from a heavy tabletop. These are just examples, but we are going to look more into the load per length, okay? So now, if we want to use equilibrium equations, we have to convert a distributed load into a resultant with direction, magnitude, and line of action. Here we see there is a body, and the load is where we call it Qx, the force, is distributed in this weird triangular shape, triangular ways, distributed. Okay, but if we find the resultant force of all of them, then it's kind of like finding resultant force. Okay, just that's all. So the direction, okay, same as the distributed load. Okay, so magnitude is going to be R, which is going to be the resultant force of the whole distributed load. Should be the integration. We use integration here because it kind of looks like integration of B, A, and the function q of x. And then we do the line of action is going to be again integration, but it is q times x here. And then we can find the xr equals the integration of for the magnitude and line of action divided by each other. This is a bit too much, but there is ways where you can just remember the equations for each form. For example, this is a triangle. There is a way to just remember, and that's it. There is rectangles, another way of finding distributed loads. So here is the how you find. So you got uniformly distributed loads and linearly distributed loads. So usually, if you have something like this, UDL is kind of like a rectangle. All you have to do, instead of doing all that integration only comes in handy when the shape is actually really weird. And what you will do is just the resultant force you will on the body, okay, will be in the middle of where the arrows are. So the length of the first arrow to the last arrow, and then you divide that length, and that's where the resultant force arrow should go. And then the resultant force will be Q. Q is the force you are given, newtons per meter. If you use dimensional analysis, you will know that if you want to find the resultant force, which is N newtons, Q, the one with the newtons per meter you are given, the distributed load, multiply that by the length where it's distributed through, and then you will get your resultant force. Now, what if it's linearly distributed load? This one looks more like a triangle. Yeah. And what we could do here, the position of the resultant force is different. It's not going to be in the middle from where it starts to where it ends. Now, first of all, let's look how to find the resultant force in the beginning. Well, what we will do again, we will use dimensional analysis. So just whenever you forget this equation, the resultant force will be Q, the number you get, newtons per meter, times the length where the distribution is distributed through on the body, and then you divide that by 2 because it's more like a triangular shape. Okay, now it really depends on the shape, again, as I said. Anyways, then to find the where it is, it will be 2 so it will be 2/3 of the length you have from the zero end, as you see there. Now, this is a bit more difficult, but if you know these equations, you will be fine, hopefully. And yeah, that's all. I hope you really understood all of this. I think in the last 2 slides, I got a bit less energetic. Maybe I didn't explain it well, but I really actually, if you felt like my explanation was not the best, you could always pause on the slide and read it by yourself. There is a lot of things written on the slide that I don't read out the slides, that's the thing. yeah, you could do that. And I don't want to make this video longer than it is. Thank you so much for watching, and I hope to see you on the next video.